In this video, we will discuss the topic of dimensionality reduction. We will discuss what dimensionality reduction is, why we need such techniques, and how to reduce dimensions of a dataset. Suppose apples and oranges are being studied. For this purpose, two features of apples and oranges are measured and saved. Those two features are the fruit's weight, and that's plotted on the y-axis, and the fruit's greenness, and that's plotted on the x-axis. After a lot of research, some researchers suggest to increase the number of features. Maybe that way they can learn more about apples and oranges. Those were the new features measured: roundness, time taken to free fall, softness, and age. The questions they face are all of those features informative? Are they all equally good? Do we even need all of them? And can we order them based on their importance? And how do we even define a feature's importance? This is where dimensionality reduction steps in. Dimensionality reduction is a set of machine learning techniques. Its purpose is to transfer high dimensional data to low dimensional data, with the constraint of keeping as much of the properties of the original data as possible. A space where we move from a large number of features to a smaller number of features. But why do we need such techniques? One of the very common problems with data is its size. The size affects the storage cost, and it also affects the complexity of processing this data. Dimensionality reduction helps in making the storage and the processing of the data more effective. Another reason for using dimensionality reduction techniques can be explained by this example here. The dataset here is called MNIST dataset. It has 60,000 images of handwritten digits. Each image of a digit is 28 by 28 pixels. The pixel values of each image are used as the features to represent the image. The features are reshaped to a 1D vector of size 784, which is 28 by 28. Each image has its label of which digit it is. The image you see here is the 2D visualization of the dataset points. The digits are colored based on the label of the digits. So all the images of digits 0, for example, are plotted in red. This is an example of digit 0 and how it is represented in a 28 by 28 pixel image, and then it's reshaped to a 1D vector of size 784. But then how could we represent a feature vector of size 784 on a 2D graph? The problem here is it is only possible to visualize 2D or 3D, so 2 features or 3 features maximum. Trying to visualize different combination of features randomly might be a way to go, but another method is to use dimensionality reduction techniques, of course. It would give you an indication of which features are more important to choose from for such visualization. This way, you choose the best possible 2 features instead of trying random feature combinations. As you can see, there are already clear clusters visually detected when showing only the 2 features chosen by dimensionality reduction techniques. So another important reason for using dimensionality reduction is the data visualization. It helps in discovering hidden structure in data. We now have 2 reasons to use dimensionality reduction. One more reason also is to remove redundant or noisy features. From this example here, adding a feature of time taken to free fall is actually dependent on the weight feature. Therefore, using only one of them is enough. Having them both will need extra storage with no extra additional information. Another reason also is we might be using more features than we actually need. From the image here, all the data points fall on one line, and we are using 2 features or 2 dimensions to represent the data, although it can be represented using only one feature instead. This is actually called the intrinsic dimensionality of the data. It is the exact dimensions needed to represent the data without losing any of the information about the features. By now, you should have a better idea of what dimensionality reduction is and why such techniques are needed.